Okay, good morning. It's good morning for me. So wherever you're watching this, this is the continuation of the October 2023 Unit 4 Edexcel International A-Level paper. And we went through question 16 last time, and I promised you that I would write it out in neat for you. So we were going through this question where the bar magnet was falling through a coil and it produced the graph which is shown here. So how you respond to this, it's about Faraday and Lenz's law. So if you look at the different parts of the graph, you can zoom in and out, you can look at it later. This is how I put my points across. So I'm just going to leave it there for a few seconds. You can pause the video and copy it out if you want to just double check that you've got the best way of answering one of these questions, which seem to be very common in this Unit 4 paper. You will need to know Faraday and Lenz's law, both mathematically, graphically, and verbally. So these are the most difficult questions, I believe. It's the 6-mark questions. Okay, so if you've used that video to go through it, we can now go on to question 17. Okay, question 17, you'll notice, is also about electromagnetic induction. Yeah. In this question, a copper rod shown in the graph as PQ is automatically is going to be moved along these rails, and the copper rod obviously is a conductor, so it's going to create electromagnetic induction because it's moving in a region of a uniform magnetic field as represented by the x's in this square. Okay, so the rod is moved with a velocity v along a pair of copper rails. As shown, the rails are a distance d apart. Okay, so basically it's only the length of the rods which will produce the EMF between the two copper rails. The rod and the rails are in a uniform magnetic field that is directed vertically downwards, so it's into the page. So calculate the EMF induced across the copper rod. Well, this is again Faraday's law of electromagnetic induction. So the rate of cutting the field is the negative because of Lenz's law, dN phi by dt. So it comes from this formula. Now in this case, you can simplify this to E equals BLV. Yeah? Now, how do you get this? So this is a shortcut, the answer. So you actually, L is the length. Yeah, in this case, L is basically the value D here. So this would be equal to L in my equation. You've been given the V, so just multiplying these three answers will get you the solution. But why is that? So what we want to look at is where is the underlying theory. So here are my notes which may help you. So the first thing you need to know is E, the magnitude of the EMF, is the rate of flux linkage, yes, the rate of change of going through the magnetic field and cutting through the field lines. So this PQ is moving on the copper rails at a velocity v, and the effective length of the copper rod is the width of the copper rails, because that's where you're going to get the EMF induced. Okay? Once you know this equation, N, there's only one copper rod, so N is equal to 1, so you can ignore the N. Phi, the magnetic flux, is equal to the magnetic field intensity, which is given to you on the previous page, multiply by the area. This is the equation that you normally know. Well, if you know, the area that is cut out is dl, yeah? Where L is velocity multiplied by time. So as it moves across, you could say L equals Vt. So if you can rearrange the equation with phi being B times d times L, where L is Vt. How much the velocity obviously moves across will be d, will be so L, which is velocity times the time taken. Okay. Now you will notice, because we're dividing EMF by time, the times cancel out, and that's BdV, which, if we go back to my previous page, is actually the equation BLV. So this is how you prove it, but once you know how to get it, now they give you marks for understanding that. So I'm just wondering if you, in the exam, if you take the shortcut, whether you would still get all 3 marks. You should do, because once you've got the right answer, you can basically show that you've understood the theory that I just explained to you. So the EMF is 150 times 10 to the minus 3. Remember, the milli means 10 to the minus 3, times the length, which is 7.5 centimeters, so 7.5 times 10 to the minus 2 meters, and the velocity is given to us as 3.5 times 10 to the minus 2. And once you multiply those values together, you actually get 3.94 times 10 to the minus 4 volts. So once you get that, you have worked out the induced EMF. Now, if you cannot remember this equation, you would have to go through this algebra. And in the exam, they want you, as long as you know that somehow you have shown that phi is equal to BA, and you have worked out that the area is to do with the amount of flux linkage that occurs, which is, you'd have to actually be able to work it out. As long as you got that you've used it along with this kind of maths, that's your first mark. The second one is knowing that you have to actually then put it into an equation which gives you the rate of flux linkage, yeah? And finally you get 1 mark for doing that, or putting numbers in that will enable you to work out the EMF. And the third mark is for getting the answer with the units. So how you do this, it's up to you. The first principles is in my notes. A shortcut, which I've taught my students before, is that E equals BLV. Okay? Now, if we just move down the page, it then says, explain the direction of the induced EMF. Well, the direction is to do with a minus sign, yeah? So you need to now verbalize it. So as you know, the minus sign is to do with Lenz's law, which is to do with the conservation of momentum. So the direction of the EMF, you can say, by Lenz's law, if there was a complete circuit, yeah, so if this was part of a circuit, you could measure the EMF with a voltmeter. The direction of the induced EMF is such that it would oppose the change that produces it. Okay? So in other words, there will be something opposing the velocity, a force opposing the velocity. So the direction, so you first need to mention Lenz's law, and you need to verbalize it. So the way I read it out will help you. If this was connected to a complete circuit, and this is the key point, the direction of the induced EMF, so they want you to talk about the direction of the induced EMF, is such to oppose the change that produced it. Okay? So you need to talk about what Lenz's law tells you. So if you stop the video, you can write down what I said, and in the next video, I will give you my written response. Or you could also say, with a current, there would be a force to the right opposing the motion. Yes? So with the current being produced, there must be a force on the right opposing the motion. So again, Lenz's law is about opposing whatever is causing the EMF that's being produced. So EMF, if you work it out, the final mark would be the EMF is from P to Q. Now a shortcut is that you could use Fleming's right-hand rule, yes, to work out which direction will the current be in. And the right-hand rule, yeah, is where the thumb is the motion, so that's in the direction of the velocity, yeah, and the field is into the page, so the current will go, you can't see my hand, the current will go down towards the bottom of the page. So if you put your thumb in the direction of the velocity, the field into the page, your second finger will be from P to Q. So you would have the current induced from P to Q, yeah? So it would be from P to Q. So that's how you get the third mark, is to work out that the direction would be from P to Q. So that's where you get the 3 marks, yeah? One is to say the EMF, one is to do with the EMF opposing the change that's causing it. One is to say there will be a force against the motion. And one is for actually working out that the EMF must be from P to Q. That means the current must also be from P to Q. That's how you get your 3 marks. And that's a 6-mark question. So I hope that makes sense to you. Okay? As I said, I will write it out in full, but I don't want to take too much time when we're going through it. I'd rather you understood the theory. So we're going over now to question 18. Question 18 is about capacitors, and it's a charging-discharging circuit. So if you put the circuit to X, the battery will charge the capacitor plates and separate it into negative at the top, because it's negative, and positive at the bottom. You can see the voltage as it's charging. Okay, a student used the circuit to determine the capacitance of a capacitor. Now I've noticed a little problem with their method, but they don't seem to have mentioned it in the mark scheme. But I haven't looked at the examiner's report. But anyway, you will have to use the data they've given you to be able to answer the question. The student connected the switch to X, as I mentioned, to charge the capacitor. So to X is to charge the capacitor. She then connected the switch to Y, so when you go to Y, so that the capacitor discharged through the 150 kilo ohm resistor. So there's your resistance value. C is your capacitance, which is presumably what we want to find out. So we want to find out the capacitance of the capacitor. The student started a stopwatch. Then she connected the switch to Y and recorded the voltmeter reading every 20 seconds as the capacitor discharged. So you can see every 20 seconds she has a voltage value. Okay? So this is a required practical, charging and discharging of circuits. They actually expect you to do it with to know how to also do it with a CRO. But as long as they give you a graph of voltage against time, a CRO is a cathode ray oscilloscope, in case you're confused. Okay, so we want to find out what is C using this equation. So here are my notes at the bottom. The notes for this question are that you need to use the equation of how voltage varies with time. Well, this is a natural logarithmic equation. V equals V naught e to the minus t over CR, where C and R are the values of the capacitors, the capacitor and the resistor in the circuit. Okay, you should know that. If you take natural logs, you can rearrange the equation. The ratio of the voltages at 2 values from the graph will allow you to then work out the time value. So if you choose a value of voltage at a specific time, you know the peak value, V naught, would be here on the graph. Yeah, the starting value. You know the resistance, so the only unknown is capacitance. Okay, so you got to be able to use this equation to solve the problem. Okay? Now, if you didn't realize that if you have ln of v0 over v, yeah, rather than v over v0, if you reverse the ratio, yeah, the negative sign disappears. It gets rid of the negative value. Now, you don't need to know that. As long as you know how to solve the problems, you had to use two corresponding values of v and t from the graph, and the only unknown in the equation is c. R is given above, v and v0 are from the graph, t is also from the graph, and if you can do the algebra, you can solve this problem without too much difficulty. Okay? So so there's the method. You've got to work out that the capacitance is labelled as 470 microfarads with a tolerance of plus or minus 10. You have to work out whether the values you put in, whether the capacitance of the capacitor is within the stated tolerance. In other words, if you get the numbers from the graph and you put the values in, are you within 10% of the 470 microfarads written on the capacitor? Okay, so use the equation V equals V0, yes, as I explained, with values from the graph for V and T, yeah? So you get T and V from the graph. Okay, you can take any two values you want. To calculate C, then compare it with your 470 microfarads. Okay, so in the mark scheme, they have taken values of 4.1 volts, yeah? So at 4.1 volts, it corresponds to 80 seconds. So they've chosen a round number in time, and they've estimated that to be 4.1 volts, okay, which is a bit more, it's a bit difficult to do. You can choose different values. I think I used a different value myself. So any two values. So once you've got your values in there, so you take their value the way that they have written it out. So you need to show that the 80 there, it corresponds to just over 4 volts. Yeah? Now I'm sure if you have a slightly inaccuracy, you will still be within the range of their uncertainty. So once you do that, remember that if you put the values in, you can go straight into my other equation, which is here, yeah? And you can take natural logs. So ln V over V0 equals e to the power of, I'm just going to go straight, sorry, I'm making a mistake there. It's T over RC, yeah? So, the way they've done it, they've put the value all in one go, so you've got to put ln of 4.1 over 12, which was the starting voltage, the peak value which you also get from the graph, is equal to 80, that's 80 seconds from the graph, over the resistance value, 150 times, sorry about that, I'm still on the last page, 150 times 10 to the 3, because it's in kilo ohms, yeah, so 150 times 10 to the 3, and that is multiplied by C. Change the subject of the formula around to make C the subject of the formula, yeah, it'll become out to 80 over 150 times 10 to the 3, and then you divide it by whatever the value of the ratio of 4.1 over 12 natural logarithms with your calculator will be, and it gives you a value using the figures that we've put in of 1.1 times 470 I'm sorry, it gives you a value of 497. just read it. I'm just copying down the wrong line. 497 times 10 to the minus 4 farads. Okay? Now they want you to compare it to 470 microfarads. So I think that should be 10 to the minus 4.97 when you put it in the calculator times 10 to the minus 4, which is approximately 497 microfarads. So that's 497 microfarads. Okay, now is that within 10% of the tolerance? So you've got to work out how much is 10% of 470. Well, 470 times 1.1, which is 10% added on, will give you 470 times 1.1 will give you a value of 517. So that's plus 10% would be equal to multiplying by 1.1. There's a 10%, becomes a 1.1. So it is within the tolerance. So you have answered the question and you've got your value to within the tolerance. Okay? Now, the next part is an ultra capacitor. Okay? Is a high capacity capacitor. One ultra capacitor has a capacitance of 47 farads, no micro in there. Okay? The maximum charge this capacitor can store is 56 coulombs. So here you need to look at your equation sheets, and you'll find in the equation sheets that the energy stored, yes, sometimes written as W, I think they use W, the energy stored is half Q squared times C. So we know the Q, we know the C. So for this question, yeah, you need to show how you can use this equation, yeah, and it is suggested that this capacitor could store 1,000 times as much energy as a 470 microfarad capacitor, which was mentioned in the previous question, the student's experiment. And the capacitor charged to a potential difference of 12 volts. So if we are looking at this time, you can work out the energy using another formula, half CV squared. As long as you show that you can get numbers into these two forms to get the two values for your energy, yeah? Calculate the energy stored for each and compare, then make a valid conclusion. So assess the validity of this suggestion. So is this equation give you an answer which is 1,000 times bigger than the equation for the 470 microfarads? So when you put the answers in, yeah, remember that for the first one, this one, the energy will be equal to half Q squared, well the Q is 56, so it's 56 squared, divided by 47, and there's no micro, remember that. Once you put those values in, you should get, according to my calculations, 33.4 joules. Don't forget to put your units in. If you then do it with this equation, yeah, for the microfarad capacitor, this time you've been given the capacitance as 470. So you then use C, and we have the voltage, so you have to use the different formula. You put 470 times 10 to the minus 6, yeah, 10 to the minus 6, and multiply it by 12 squared. When you can see that obviously minus 6 is going to make the energy much lower. The energy value, when you put those in your calculators, will give you a value of 0.0338 joules. Okay? Now you want to divide this energy by that energy. So E1 divided by E2. So E1 over E2 is 33.4 divided by 0.0338, which comes out to approximately 987, which is approximately equal to 1000. Therefore, assess the validity of the suggestion. Say their claim is valid. Okay? And that will get you the 3 marks. So one is for working out this energy, one is for working out the second energy, and one is for assessing the claim using the ratio of the values. Okay, well that's taken us to the end of the next video, and I hope you found it useful. And there's just a few questions left to do, which I will do in a follow-up video. Just make sure you subscribe so you know when these videos are released. Okay, thank you very much, and please share and like the video with your friends. Like it, share it with your friends so we get more of a following that will enable us to produce more such videos in the future. Thank you very much.